Hi, you can hear me?
Yeah.
Okay.
Can you see me?
Yes, I can see it. So we are going live. Okay, we are live, yeah. So we wait for one more minute and start.
Yeah, sure. That
It's
sounds
like
good.
4:39, so we will start at 4:31. Good. So, Sai, can you hear me?
Yes.
Yeah, good. So we are live. Welcome everyone. Today again, I welcome you to our faculty seminar that this time will be given by Professor Sai Vinjanampathy. I hope the stream is live and everybody can see us. We'll follow the similar pattern like last time. We will go through the talk, and in the YouTube chat box, you can type your questions live, and we will be able to answer those questions. That's number one. Number two is after the talk ends, we will be still live streaming the question answer session. And at that time, I will post the link of the Jitsi room where we are essentially. And you can enter, but please enter only if you have a questions. Also, when you will enter, you will be muted to begin with. So you unmute yourself, question whatever the question is, and please then you can leave it because we don't have a large bandwidth to keep too many people there. Okay, so with this small thing, let me start. So it's my great pleasure to welcome Professor Sai Vinjanampathy for our second faculty seminar, virtual faculty seminar. So let me just introduce him slowly. So he did MSc from IIT Madras in 2004. So if you guys were there in the previous talk, Uma was there, and Uma was also from IIT Madras. I am also from IIT Madras. It's a little bit of advertisement. Then he went to do PhD in LSU, Louisiana. He did his PhD in 2010. After that, he did two postdocs, one in UMass Boston, and then the second one was at CQT, Center for Quantum Technology in Singapore. And then he moved to IIT Bombay in 2016, and from then we are together. So Sai, it's a great pleasure again to welcome you, and he's going to talk about many-body quantum control on NISQ devices. So I will mute myself, and I will also mute my video, means I will stop my video. So whenever you need to ask me a question or anything, Sai, just let me know, yeah? Okay.
Thank you very
The
much.
stage is to you.
Yeah. Thank you very much, Shomo. Thank you, everyone who's attending. It's again a great pleasure to kind of report on what I've been up to. So today I'm actually here to talk to you about a very specific problem that I've been working with Guru and Tejas, both of whom are in the department. And it tries to answer a simple question, which is, can I do quantum control on a quantum computer? This is essentially the entire question. And so to do that, I understand that we have a very diverse department. And so what I want to do as an outline for the talk is basically give a quick introduction to control strategy, so you don't have to bring anything with you. I'll introduce everything that I need. And I'll talk about one control algorithm particularly, which is what this famous algorithm called the Krotov algorithm. And I'll talk about how you will run into issues if you try and do quantum control of many-body quantum systems with it. So I'll talk about the bottlenecks. And having set up the problem, so point number 2 and 3 are are set up the problem. I'll try and tell you what our approach is to solve the problem, essentially. And there'll be a little bit of technical stuff in there about superposition and interferometry, and then I'll put it all together and conclude. So like Shomo said, please feel free to ask questions anytime, and I'm happy to be interrupted. Okay, so let me get started right away with an essential review of control theory, the control theory that I need for this talk. Um, and so let me begin by saying that, often I try to introduce the problem in the following way by saying that what we are used to doing in standard quantum mechanics, this is what I learned as a student, and also this is what we typically teach in a first course on quantum mechanics, is what I would call the forward problem. And the forward problem is that I give you a Hamiltonian H, which depends on some control fields B of t. I also give you the control field B of t. So I'm not asking you to do anything. It's just I prescribe, let's say, a sine wave or something like that. And I give you an initial state. Maybe I give you a time t, and I say, please find at some time t what my quantum state is. So this is just the forward problem. This is, when we solve, when we study things like time-dependent Schrodinger equation, time-dependent perturbation theory. This is what we're doing typically. But there is another variety of problems which is actually more interesting to us and more interesting from an engineering perspective. And that is, given a Hamiltonian H, which depends on some control fields B of t, given an initial state and a target state tau, right? So this is the new thing here, a final time t, and maybe an optimization criterion, right? Definitely an optimization criterion. Can you please find the best B of t that gets me from the initial state to the final state, right? So this is asking the question in in the way that it actually makes sense, right? So for instance, we are in Bombay right now, and I would ask the question, what is the cheapest way to go to Pune? I would not ask the question, the forward problem is something that I typically don't ask, which is, if I get into this bus, where will I be in 5 hours? This is not something that's typically interesting to all of us, right? So from that perspective, hopefully the inverse problem motivates itself. It's actually what you want to do is tau, and the amount of ability that you have to do it is the Hamiltonian. So what does this look like when you try and draw pictures? In pictures, what does this look like? So here is some typical control that I give you. So this left-hand panel is the forward process. And so I give you, let's say, some control field as a function of time. So I haven't even marked the axis because it's just an illustration. And in state space, I start at some initial state psi naught, and I say, well, where am I as a function of time? So you're trying to figure out what the trajectory is. On the other hand, the inverse problem essentially looks like the following. It says, I have an initial state psi naught, I have a target state tau. Can you please tell me how to go from the initial state psi naught to the target state tau? And so maybe there exists a solution here, and when the solution does exist, maybe the control field is very difficult to imagine, without a kind of proper structure to solve the problem. So the entirety of quantum optimal control theory basically tries to set up this inverse problem solution for quantum mechanics and tries to solve it, right? So that's the solution. So just a kind of as a cartoon, again, I've drawn the original trajectory. So if I had chosen, some arbitrary pulse shape, I wouldn't get where I want to go. I actually need to engineer the pulse shape. I need to carefully think about how to do it. So before I give you the technical aspects of control theory, so I just want to introduce the field to you by saying there are various questions you can ask, and depending on the questions you ask, there are various categorizations of what control theory looks like. So I could ask, for instance, what do I want to control? Do I want to control quantum states, or do I want to control unitary operators, right? So which are called quantum gates in quantum computing. I could ask a different question. I could say, what is the inherent dynamics? Is it closed, which means the underlying dynamics is well described by Schrodinger's equation, and I don't need to worry about dissipative processes? Or is it open, which, in the quantum mechanical setting basically is slightly subtle. It's you have to do a little bit more work than just writing, let's say, a damped harmonic oscillator. I could also ask, what kind of optimization am I performing? What are all the things that I'm trying to optimize? Am I trying to fix the time and optimize, let's say, getting as close to the target as possible? Am I trying to find the minimum time that it takes to get to the target? Am I trying to impose bandwidth constraints? So this is something which is experimentally very relevant and something that I've been thinking about recently. And do I want to do something like fluence control, which basically controls the total amount of power that's going into the system? I'll explain this term in a little bit. Mathematically, I'll describe it as well. So in today's talk, actually, what I'm going to talk about is basically, I'm going to take on the stuff that's in green and also the stuff in blue I'll talk about a little bit. So I'll talk about closed quantum systems. So I only need to worry about quantum mechanical states. And I'm going to talk about a fixed time optimization algorithm, which incorporates basically this power control inside it. So I'll also talk a little bit about bandwidth constraints. I'll imply them, and minimum time also is implied in some of the work that I'll show you. But I won't talk about them explicitly anymore. So with this, I just want to also tell you that you can write this entire thing mathematically. So, what I've just said to you in words, I can write it mathematically. So I could say, produce a B star, which is the argmin of B, which belongs in a set B, that basically minimizes some distance D, right? It's in words exactly what I just said a second ago. So let me just go back to the figure that I had. So it says, give me the optimal field that basically minimizes the distance to its target state, right? That's all that this mathematical formula is trying to say. And inside this, basically, you can incorporate the bandwidth constraints, the amplitude constraints, and the fluence constraints, which is just the integral square of the magnetic field that you're using. You can incorporate all of these things into the allowed set of controls B, this curly B. So this allowed set of controls curly B actually encodes all of the allowed bandwidth constraints, allowed bandwidth that you're allowed to operate in, the amplitudes that you're allowed to operate in, and so on and so forth. So just a quick point before we move on, because this will become, this term will appear in other equations, and so I just want you to be comfortable with it as well. Why did I choose integral of B square, right? In fact, it's quite simple to understand that I would want to try and set up a control theory where I minimize the amount of magnetic field that I'm using, right? So, or any control field for that matter, because what you don't want to do is put too much power into the system, which might basically heat the system or pump the system in ways that are undesirable. So, but why mathematically did I choose B square and not B? This is actually evident here. So on the x-axis is the magnetic field. I've just set it to a constant number for now for illustration. I've chosen B, and on the y-axis I've chosen two functions, B and B square. If I choose just the linear B, then the minima, the smallest amount of B that I use is at minus infinity. And as I will show you in a second, this will overwhelm all of the control solutions that we try and propose. So the linear B basically has this small problem that its a minima is sitting at minus infinity. So if you choose absolute value of B, which has a discontinuity at the origin, so if you choose B squared, then that is well behaved. You can see, that the origin is basically the minimum value of B. So the minimum value of B is in fact well enforced by the B square constraint. So that's the clarification I just wanted to give you there. With that, basically, let me again state this problem now in terms of pictures. So I'm bringing the two things together. One was the kind of simple intuitive picture that I showed you, and then the formula. And what you can ask is the following. You can say, I have an initial state psi naught, I have a target state tau, and I have some set of points that I can access in state space. Can you please produce for me the best algorithm that gets me basically the closest to the target state tau? So I've called this distance D, and you can measure it in whichever way you want. There's a number of ways in which you would measure such a thing inside quantum mechanics. So trace distance, for those who are interested, is something that's commonly employed. Fidelity is another measure. Now, on top of it, what we're going to do is basically, we could ask for additional constraints. So here are a bunch of paths which basically all take you to the same point. But I have highlighted this one in thick lining, basically to indicate that maybe there are additional things I want from my optimization. I not only want you to get me the closest to the target state, but I also want you to do it in a way that that expends the least amount of magnetic field. So maybe this one consumes the least amount of magnetic field. So it's a kind of multiple optimization problem that we are actually quite familiar with in physics, right?
There is a question.
Yes.
From Sumiran, I'm reading it. So are we assuming that any value of B of t is achievable in this optimization?
No. So in this specification, B curly B, that actually constrains you in the allowed set of magnetic fields. So, for instance, I'm only allowed, let's say, I have some kind of superconducting resonator, and I'm sitting at some frequency, and I'm only allowed 200 megahertz plus minus. You can encode it into the set B. And by encoding it into the set B, you can actually get a constrained optimization problem. So how you would solve this mathematically is a whole other story, but problem is well posed at this point with respect to kind of not allowing for unphysical magnetic fields. So
it's essentially given from the experimental perspective. So in experiment, let's say you
yes,
have this much of bandwidth or whatever, and you are constrained by that.
all of
This,
that. So there are kind of experiments in chemistry where if you kind of you can undergo photo dissociation. So you want to make sure that that your fields are basically constrained in a way that you don't lose the product. It doesn't become basically, it doesn't dissociate. So so things like that. So there can be very varied experimental constraints that you can incorporate into this allowed set B. So that's the way you would set up the problem.
thank you.
So let me just say, typically the way this works in the field of control theory is you just solve the unconstrained problem, and then you try and basically apply constraints on top of it by doing some other things, which I can talk about offline.
Okay, thanks.
Okay. Any other questions, Kamu?
Not yet, not yet.
Okay. Let me. Okay. So with that little introduction, let me talk about one specific algorithm that actually is quite famous for doing optimal control, and it's called Krotov's algorithm. And so, as a side note, before I introduce Krotov algorithm, I just want to remind also the students who may be listening in that variational optimization, which is what I'm going to use, is something that all of us know and know it quite well. So here is basically the action. Typically, we write the letter S for it, but I've just written the letter J. And it's given as basically some integral of some Lagrangian. And what we would do is we would say the principle of stationary action demands that delta J is equal to 0. And the way you would impose that is you would take the two derivatives here, delta F and delta F prime. And what you do with delta F prime is you just do integration by parts, and you throw away there is no variation in the corner, so you throw away this term, and you end up with a minus delta by delta x times del L by del F prime. And if you plug it in here, then del L by del F and delta by delta x del L by del F prime is basically just Euler-Lagrange equations, right? So in one small step, what I want to introduce to you, or what I want to remind again, especially maybe students who are listening in, is basically that we are used to thinking in standard classical mechanics, quantum mechanics, and everywhere else. We're used to thinking of cost functions, J. I'm going to introduce to you a cost function, and I don't want you to be surprised by it, and first order variation, delta J equals 0, and the corresponding Euler-Lagrange equation that comes out. These three things we've already seen many examples of. And in fact, the standard derivation of Euler-Lagrange is a classic example of this, right? So with that little reminder for all of us, let me show you the cost function that Krotov wrote down. So Krotov's cost function J is basically that at the final time, the quantum state must be as close to the target state as possible. So this is what is called the quantum fidelity, and it's just the overlap between the two wave functions mod squared. So it's like the probability of being in the final state. You want to basically minimize because you want to maximize J, you write this down. The maximum value of the first term is 1. The minimum, you want to minimize integral 0 to t b squared. And the minimum value of it, of course, is at 0, but you at 0 control field, then you don't do anything. So you want to increase it a little bit to get this done. And the third constraint that you want is you want to maximize this, minimize this, whilst obeying Schrodinger equation. It's a classic variational problem that we actually see quite often in physics as well. And the way you incorporate this, this is by bringing in a Lagrange multiplier. So this chi that you're seeing here as a bra is basically a Lagrange multiplier. So let me just remind everyone that when you're writing a cost function, it's a scalar. And when you bring in basically a vector quantity, which is basically that del t psi dot is minus I h psi. And what you mean by that is that del t plus I h t acting on psi must be the null operator, must be 0. And if it is 0, then that vector of zeros essentially is the Schrodinger equation being satisfied. You bring that constraint in by another vector, because you take the inner product of two vectors and it's a number, and you can put it into a cost function, which is also a number. So that's the way to think about it. And so that's the cost function. It's a very classic cost function that optimal control in the optimal control literature.
Sorry, I have a question.
Yes.
Sorry, it's from my side only. So
yes.
This type of variational theory does not always allow you to go to the global minima, right? So you may have a situation you can be stuck in a local minima, and how do you get rid of it?
Almost always. Almost always. So you almost always end up with a local minima. The way to do it is just the way you do it everywhere else, which is you do stochastic restarts. You start the problem again and again with various initial
I
conditions, and you
see.
check if you're running into other minima. Let me say with this caveat that Krotov actually produces incredibly good results.
I see.
It's well known to produce, So if you try to do other methods, so there's another method which I have in the overflow slides if I have time. If you try to do other methods like grape, basically, typically what happens is that if you start at a bad starting point, you don't get anywhere near the initial near the value that you want. So
I
what do
see.
you want? You want basically the overlap to be near one, as close to one as possible. If you start the gradient methods, the other gradient methods in a bad place, if you start at point 2, you end up at point 3, right? So it's quite bad. You could have guessed your way to point 3 actually, but whereas Krotov, if you start at point 2, it will get you to 0.95 very quickly. So
Oh.
Krotov is quite well behaved in that way, even though it's a local minimization problem, technically speaking.
Okay, thanks.
Okay. Okay, so to come back to this, so again, I will demand first order variation. And now, what are the independent parameters? Just like we had f and f prime as being independent parameters, the independent parameters here are the state, the co-state, the Lagrange multiplier chi, and the magnetic field B. And for brevity, I've left out the time dependence. All three of these are time dependent quantities. And if you set them to 0, you get 3 equations. And those 3 simultaneous equations of motion are the Krotov solution, basically. And we have to implement that. And so it looks like this. So let me point out several very interesting things about this. The first of it is basically that the first equation here is just Schrodinger equation. It says I psi dot is h psi, given the initial condition psi naught. So this is just a forward time Schrodinger equation, nothing surprising or complicated about it. The second equation is basically the equation that the co-state, the Lagrange multiplier, obeys, and its I chi dot is h dagger chi, and with a terminal condition, which is that chi at the terminal point at the final time t is proportional to the cost function, the target that you're trying to find. So let me, and then there is a third equation, which is that the magnetic field B is the imaginary part of an overlap between chi and psi. So let me just take 1 second to quickly remind us as to about the slight strangeness of some of this. One strange thing is that I've written H dagger, even though I'm just doing Schrodinger quantum mechanics, which means my Hamiltonians are absolutely a Hermitian. And the reason why I wrote H dagger is basically to remind myself that in the open quantum system case, this is a slightly technical point, this H is replaced by basically a Liouville space operator, which is not Hermitian. And so this H dagger starts making a lot of subtle difference about dissipation going forward in time and backward in time. So it's basically this dagger catches the fact that quantum mechanics, closed system quantum mechanics is time reversal invariant, but open system quantum mechanics has semi-group dynamics. So that little subtle fact is caught by this dagger. The second thing that I want to point out is that this chi doesn't start at the initial time 0. It starts at the final time t. The Schrodinger equation is running backwards in time. And this backwards in time Schrodinger equation is basically a very classic hallmark of all variational principles. So I just want to point this out. And the third is basically the difficulty in solving this problem. So as you can see, the magnetic field depends on the wave function, and the wave function depends on the magnetic field. So you need one to find the other. And essentially, this is a problem that we've encountered before. For instance, we've encountered this problem in Hartree-Fock theory, right? So you want to write down basically the local charge density, which depends on the wave function. And to solve the wave function, you need the local charge density. So that kind of an issue. So the way we solve it is by basically making an ansatz and algorithmizing the problem. So again, this is something that we know very well from solid state physics and condensed matter theory literature. And one thing I just want to point out here as well is that this operator mu is just whatever is appearing in front of this control field B of t. So this mu is just I'm going to just call it mu and for the dipole moment operator basically. And I'll show you something important related to that. So I understand that this is a lot to take in. So I apologize for this slide especially. So this is a slightly more complicated version of the Krotov algorithm. So just take delta equals 1. So if delta is 1, this delta switches on and this is switched off. And if eta is equal to 0, then this is switched on and this is switched off. And this xi k just becomes xi tilde k, and xi is just what I was calling b. This is just from one of my papers a couple of years ago. I was just being a bit lazy. But what I want you to see is the following important thing, which is that I break this problem that I had, which is that I couldn't solve the right hand side because I needed the left hand side, and I couldn't solve the left hand side because I needed the right hand side. I solved this problem by basically doing something clever, and the clever thing is I simply break one of them and replace it with a previous iteration. So I've brought in this number k, and k is basically the number of runs of the algorithm that I'm doing, just like Hartree-Fock, just like many other algorithmic methods inside quantum mechanics. You run this once, it produces a solution. You run it again, it produces a better solution. You run it a third time, so on and so forth, till it converges, basically. So what I'm doing is I'm taking the previous value of the co-state and the current value of the state, and I'm trying to evaluate this magnetic field here, right? So this is just the generalization of the magnetic field. So because that's again a lot of equations, this is what it looks like in a picture. So you guess the initial state, you just guess some random field basically. Typically people either put in 0 or a bunch of random numbers, and then you update the quantum state, you update the co-state, and then you calculate basically the new magnetic fields, and then you rinse and repeat till you hit convergence, and at which point you can terminate. So the only things that I want you to carry away from this slide are 4 points. The first point is you have to update the state, and it's a forward time evolution. The second is you have to update the co-state, and it's a backward time evolution. This is the Lagrange multiplier. And the third is that you have to update the field, right, by using the overlap equation. And the fourth is you have to repeat this over and over and over again, right? So this is the computational cost of trying to solve optimal control problems on a computer. And this is the reason why I just want you to take away these 4 points. That's it. Everything else you can forget. So before I move on, let me just show you very quickly an example of this. So this is the cost function J. It starts with a random guess. It's basically a thermalization problem. It's not particularly important. And as you can see, it very quickly converges to a very high value of the cost function. And what I'm trying to do in pictures is basically I'm trying to minimize some distance. And if I don't do anything, this is how the distance evolves. It evolves somewhat gently towards the target, but I can, by using optimal control, I can speed up basically this distance. I can close the gap on this distance. And the corresponding control field B looks like this. So it's actually a little bit complicated, even though it just looks like a sine wave. If you Fourier transform it, it has some slightly weird frequencies in it, which are illustrative. So typically, the point I just want to make is that typically the control solutions that are produced are very counterintuitive, and it's not very easy to just simply look at it and derive an analytical result for it. So you have to go through this procedure to find these kinds of solutions. Okay. So that was my introduction to Krotov. So are there any questions before I move on to the next section?
No, sir,
Okay.
Not
yet.
Not
okay,
yet.
so let me move on by saying, okay, now what I want to do is I want to do this for a large quantum system, a closed large quantum system as my first order approximation. And so I'm going to talk about what happens when you have n qubits here, right? So this is what happens when I approach trying to solve this problem for order 2 to the n. So the thing that I'm going to talk about is, the hurdles that I'm going to talk about are true not just for gradient-based approaches, but also for machine learning approaches, which is something else that I have an interest in. So the existing issues right now are basically that analytical gradients are better, but computing them is a little bit of a complication. Hessian complexity goes as order n squared. So if you say, okay, I just do gradient ascent, or I do this kind of variational theory, then you need to compute sometimes first derivatives, sometimes second derivatives, and computing these derivatives analytically becomes very complicated because they grow as order n square in the number of controls that you have. So if the number of controls are large, then this is not good, right? This is already problems that that we have, but we have a new problem that has come up in the formulation of my problem. My question, which is that if the underlying quantum evolution is also hard, so if I have many body physics underneath, then this whole thing is much worse. Basically, this is a really, really hard problem to track because you can't even complete one evolution cycle in a reasonable amount of time, right? So this is the problem that we want to take on. So what solutions exist? The existing solutions for this large Hilbert space problem are mean field theories. So you can say, okay, I forget about trying to simulate the whole dynamics. I take basically just the mean field dynamics and I try and construct a control theory on it. You can do that. It has the same problems that cumulant expansions have, which are just a generalization of mean field theory, which is that you will miss important correlations. So the moment you do that, you basically can miss important correlations. And you can do, there is a lot of progress you can make with this, but it's restricted for these reasons that I mentioned. You can try modular optimization techniques, which is basically something that again is of interest to me, where basically what you do is you approach the problem by breaking it into small quantum systems and then couplings that you can handle somewhat. And there's one more technique which I forgot to write here, which is tensor product methods, basically. So you can either use DMRG or tensor product methods, which are actually quite common these days to do, but they're a kind of approximation theory as well. So control solutions are bound to be limited, and especially the point I'm trying to make is you can't get very far with this, basically, especially for exotic quantum correlations. Okay, so I'm roughly at the half-point mark. So let me talk about our approach. So we basically said at this point we asked ourselves the question: what can we do if you had access to a small quantum computer? What can you do with or even a large quantum computer? What can you do? Can you do better? And the problem at first, maybe you can say, well, what's the problem? You have a large quantum computer, so you should be able to do everything you want. But there are some small subtleties which I want to point out, and that will be the solution that I will propose. So again, let me just state the problem once more, just for clarity and to remind ourselves. So I want to design a quantum optimal protocol that is optimal, and optimal with a star is locally optimal. That takes basically my initial state psi naught to some target state tau in some time t, right? Following a set of optimal procedures. And following Krotov's algorithm, I have to solve, what this means is I have to solve the following three equations. I psi dot is h psi with an initial condition. I chi dot is h dagger chi with the terminal condition. Sorry, there is a small typo here. There should be chi at capital T, right? And there is basically the field update equation, which is this imaginary part of this overlap that I have to do. So what are the challenges in front of us? Let's recall what Krotov algorithm is, right? So this is what Krotov algorithm, so these three basically are the three equations that I just presented a second ago. So the challenges in front of us are that we have to evolve something forward in time, and we have to evolve something backwards in time, right? So those are the two challenges. And the third is we have to evaluate this overlap integral. So there are three challenges in front of us, two of which are unfolding into one as state evolution challenges. And the third challenge is basically the overlap evaluation challenge, right? So the hurdles to overcome, this is what I've just said in words here, is first I have to figure out how to run these simulations, basically. And the second is I have to basically figure out how to compute overlap integrals. So I have to calculate, for instance, the overlap between the target state and the final terminal state. And I also have to evaluate this overlap, which is sitting inside the Krotov algorithm, right? So what I will propose in front of you now are the two solutions, basically, that we've come up with to solve these two problems. There is this other problem, which is that this is all complicated by the exponential size of the Hilbert space, right? So this is what this slide explains. So again, just to kind of say it in words, what are the bottlenecks? The bottlenecks is exponential Hilbert space, which means that you have to have exponential a capacity to basically simulate something that is in an exponential Hilbert space. Second is you need to extract very specific time series data, right? Because what you need to do is basically you need to evaluate, for instance, this overlap, which is a time series, this overlap, which is basically one number. So you need to evaluate a bunch of overlaps, which are basically time series data. And you need to implement all of this on a noisy intermediate scale quantum computer. So I'll mention what this is, but just think of it as a noisy computer for now, right? So these are the three bottlenecks, and I'll try and resolve these three bottlenecks in the next 20 minutes or so. So step one is basically we have to basically figure out how to do the simulation, right? So how do I do the simulation? So what we propose is basically that you instead of trying to basically run this on a computer, So this is the reason why we are trying to run this on a NISQ. You try to get the quantum computer to simulate itself, right? So this goes back to Feynman's idea that basically quantum systems are very, very efficient and good at simulating themselves. So we can set up basically a quantum system which has which can emulate basically a Hamiltonian, which has the correct control fields that are the ones that we're interested in, right? But this is tautological, because if you don't have that set of controls, then you wouldn't be interested in this problem to begin with. So it's essentially self-referential, and so it's not a we don't think that this is a huge problem. And you can trotterize it if you want or not, and I'll just leave that for the sake of the discussion length. So the first step, I ran through it pretty quickly, is basically, instead of trying to do this, instead of trying to solve the problem, just get a computer to simulate a quantum computer to simulate it. So you just take, for instance, a Bose-Hubbard model or whatever, and you just let the cold atomic system simulate itself. So you just run it to some time t, and then you have the wave function at some time t just sitting in front of you. Now the only question is, how do you extract this information from it? So that goes to the second point, which is, consider the issue of computing basically the overlap integrals, basically, right, between psi and chi. So I want to know the overlap between two quantum states. It doesn't matter what these two are right now. This is the target and this is the terminal quantum state. Again, this typo has been carried over from the other slides. But I want to evaluate basically the overlap of two operators. Without having access to those operators, right? So an unsaid thing in the previous slide, that I forgot to say, was that the problem with quantum evolution, especially the problem with trying to simulate many body systems, especially basically if you increase the size of the problem, is that you can't actually, once you have the density matrix in front of you, you can't measure it, right? Or the wave function in front of you, you can't measure it, because if I have a large number of atoms in front of me, I can't just try and figure out what psi1 is, psi2 is, psi3. The elements of the wave function are in some basis, because that's an exponentially large number of numbers I need to know, and that's a large and hard problem as well, right? So this is basically the problem of state tomography, and the problem of state tomography basically is that to characterize a density matrix, or to characterize a wave function, requires n numbers, right? N complex numbers. To characterize a density matrix requires n square, and so it's not scaling favorably, especially if the underlying number n is 2 to the power of the number of qubits. Then this is a huge number of parameters you need to establish, and so this is not the way to do it. You don't want to just simulate to some time t and then try and measure your way out of the problem. This is absolutely going to produce wrong answers, unfavorable answers. So what we propose essentially is an old technique that exists in quantum information theory, which is what's called interferometric estimation, or the swap test, as it's called. So what I've presented in front of you is the circuit diagram from the original paper. It's a Hadamard transform. So what this does is it takes 0 to 0 plus 1 over square root 2, and 1 to 0 minus 1 over square root 2. After that, it's a controlled swap gate. So if this control is switched on, if this qubit is spin up, then the swap happens. It swaps whatever is here. So I put one state psi here and state phi here, and it just swaps them. If this control is switched off, if it's spin down, then it does nothing. It just lets it go. And then I measure basically the quantum state at the end. So this, and this is the point I want to make. And so how does it implement the swap test? I'll show you the proof. It's a couple of slides worth of proof. But before I get to the proof, what I want you to take away from the slide is that wherever I see overlaps, I replace them with this test, with this swap test. So how do you do this? Just remember the Fredkin starts with an F, and here is the proof. So it's exactly the same circuit diagram. I just drew it by hand. And what I can do is I can compute basically the density matrices at R1 and R2 and R3. And it's just simple algebra, essentially. What you do is you take the initial state, because it's a Hadamard, Hadamard takes 0 to 0 plus 1 over square root 2. This is the density matrix version of it. Tensor product with basically rho ij, which is any density matrix rho that is input into this channel. And sigma alpha beta is any density matrix into this particular channel. And so that's just a basis expansion of rho and sigma. And if you just do the algebra, it's in front of you, in a couple of lines, you can prove basically that you can compute trace of rho times sigma, right? But what is trace of rho times sigma? If rho is the outer product of two vectors psi psi, and sigma is the outer product of two vectors phi phi, then this estimation method, actually what it estimates is psi phi mod square. So this mod square is very important, because remember what I tried to start by computing. I tried to compute just the overlap of two vectors, not the modulus square of it. So I need the complex number in front, right? That's a complex number in general, and I need to know what the amplitude and the phase of it is. So I need to know these two numbers. So this doesn't look like it solves the problem, right? So hopefully this problem is very clear to everyone. The solution to this problem is actually a modified swap test. So instead of sending in rho and then psi or phi, if I send in rho and then a superposition, which is psi plus phi over square root 2, into essentially this giant interferometer, then what happens is that the overlap, you can calculate what you measure, you can calculate is actually the real part of the overlap of psi rho phi. If you put a minus I times phi, I think, then it's the imaginary part here. So the real and imaginary part of any overlap between a density matrix and two wave functions can be estimated very, very quickly by simply doing this kind of a modified swap test. So now we've seemingly solved one problem, right? So now the second problem is, how do you produce a superposition? Because this superposition is again between two states that I can't describe, right? Because they're complicated states. Let me just go back 1 second. They're complicated states that are the terminal condition of a state evolution, psi k at the final time t, and the target state tau. And and so I have copies of the target state tau, and I have copies of the wave function psi at the final time. How do I evaluate the overlap between them? This, the superposition between them. This sounds complicated. And so the way we do it is basically by doing this, by employing an ancillary qubit. So the way you employ the ancillary qubit is, suppose, I don't know how, but just imagine for a second that I give you this state S. And this S is 0 psi plus 1 phi, right? Then if you apply just again a Hadamard transform on the first one, so you employ basically 0 psi plus 1 phi, 0 goes to plus, which is 0 plus 1 over square root 2, and 1 goes to minus, which is 0 minus 1 over square root 2. Then the corresponding quantum state is basically 0 times psi plus phi and 1 times psi minus phi. So we've reduced the problem basically to simply constructing these 0 psi plus 1 phi, right? And so post-selecting on 0, so if I just measure the first qubit and whenever it's 0, I let it through, then basically I simply get psi plus phi over square root 2. So this is very easy to produce. Now, what I've done is I've taken a complicated problem, which is estimating the overlap between two wave functions that I can't describe, but that are in an experiment of mine. I've converted that to basically constructing the modified swap test. The modified swap test requires psi plus phi over square root 2 as the input, which I have then converted basically to constructing the state S, right? So if I can show you how to construct the state S, I've, by just the two-step procedure, I've solved the whole problem, right? So the way to do this, I will get to that in a second, but let me just put the solution together and say that the way to do this is, so this is the consolidated step 2, is basically you replace trying to estimate wave functions with an actually interferometric measurement, which extracts only the time series that you're interested in. So it doesn't actually waste resources trying to estimate the full quantum state, which is in an exponential Hilbert space, but only estimates the time series you're interested in. So that's the solution that we're proposing. How to do the how to solve this problem of estimating S? It's just I'll present it to you below. But let me just keep moving to complete the solution. The next part of the solution is, how do I solve this overlap, right? So what I showed you before was solving the problem of a state psi with a state chi, the overlap between a state psi with a state chi. But now I don't have the overlap between a state psi and a state chi. I have a sandwich of it with some Hermitian operator mu. How do I solve this problem? The problem again is solved by a simple technique, which is that all operators are related to states. For those who are in quantum information, I point out that this is not the Choi isomorphism. So all operators are related to, all Hermitian operators are related to quantum states in the same Hilbert space by a very simple trick. And the trick is the following. Suppose I take the operator mu and I ask, why is it not a density matrix, right? Hermitian operators, which are operators that enter into a Hamiltonian, have real eigenvalues, so that property they share with wave functions and density matrices, but they can have negative diagonals, and this is the problem that they have. This is problem number one. Problem number two is they can also have basically their trace is unbounded. So you solve both problems by proposing a density matrix rho of mu. And what is rho of mu? You simply take the Hermitian operator mu. You take the largest minimum eigenvalue, negative eigenvalue you have, and you add it with an identity operator. So now you've shifted everything up, right? So suppose I have an operator 2 whose diagonal elements are 2, 0, 0, minus 2. I'll show you that in a second. Then what you're doing is you're adding 2 to everything. So you're getting 4, 2, 2, and 0. And now you divide by the trace of the operator, and now it's a density matrix. So there's nothing that differentiates this from a density matrix. So this mapping basically is something I'm going to employ. Yes, Shoma.
Yeah, so I was wondering, so until now you haven't really specified the Hamiltonian, right? So which is just at the level of states.
I have specified the Hamiltonian implicitly because it's sitting basically in the description of my of this thing. So this describes the Hamiltonian, and so the
Yeah,
Hamiltonian is specified.
I'm saying that in an explicit form, how it looks like, really how it looks like
It
is it?
yeah, this works for any Hamiltonian, but let me show you an example or two.
Okay, okay, thanks.
Yeah. So here is an example. Actually, it's in the very next slide. So how do you convert operators to density matrices? So what does this mean? So suppose I want to evaluate chi. What I want to evaluate is chi mu psi. Right. This is what we want. This object is what was the third equation in the Krotov algorithm. What I do instead is I evaluate chi rho psi, because rho is a density matrix, and I know how to evaluate that. If once I've evaluated it, I just need to evaluate one more number, which is chi identity psi, but that's just the overlap of two. So this overlap and this overlap are both things that I can experimentally implement. And so I can implement those two, and the difference of them with some little bit of algebra is just the thing that you want. So the thing that you want, which is chi mu psi, is just the trace, which is just some normalization factor, times chi rho psi minus lambda min times chi psi, right? I just want to point out, because you are choosing the local Hamiltonian, the control Hamiltonian, you can easily evaluate what the lambda min is and what trace is. So here is an example in answer to Shommo's question partially, which is let me take basically some sort of Ising chain, basically with just I switch on basically a Z magnetic field. So Z1 plus Z2. So I have the same magnetic field switched on for all the local, just a local control basically, but it's a homogeneous magnetic field that I've switched on. And so the operator mu is Z1 plus Z2 if I just have two of them. And I can write down what this is in matrix form. It's 2, 0, 0, minus 2 diagonal form. And now I can actually construct what the rho mu is by adding 2, 2, 2, and 2 here, all four diagonals. And then this becomes 0, and this becomes 4, 0, 0, 4, 2, 2, and 0. And divide by 8, and I get 1/2 times up, up, 1/4 times up, down, and 1/4 times down, up. All this mixture you can construct on a quantum computer, and you can just feed it into the solution, into the algorithm. So this brings me to the very last problem, which I will solve in the next 1 or 2 minutes, which is how do you construct basically this 0 psi plus 1 phi? How do you construct this arbitrary superpositions that you're interested in? So what I demand is basically I'm demanding some sort of weird Hamiltonian unitary operator C times U, which is a control unitary CU, and CU has the following property that if I give it 0, 0, it constructs 0 times psi. Think of psi, just for purposes of keeping up with the talk. Think of psi as my wave function psi, my state psi, and think of phi as the co-state chi, right? So if I give you 0 in the first qubit, it constructs the state. If I give it 0, 1 in the first qubit, it constructs the co-state, right? How do I construct this? What is this control unitary? This was actually solved by well, before I show you that, let me just show you that this circuit diagram actually solves this problem. So if I take my wave function at any arbitrary time psi k of t, it's some unitary operator acting on the initial state. If I take chi, basically this is the backward time evolved operator acting on the target state tau. then what I can do is I can simply take UK and VK, which are these forward and backward propagating operators, and I can switch, I can write this particular circuit diagram. And what this circuit diagram does is this open circle that this open circle that I've just shown here implements U if this state is 0, and this closed circle implements V if this state is 1. So if I send 0 in here, this switches on, this doesn't do anything. If I send 1 here, this doesn't do anything, this switches on, right? And by implementing this, you can verify basically that this circuit diagram actually just constructs the thing that we want, which is 0 psi plus 1 chi. It constructs this arbitrary superpositions of these unknown quantum states. So the very last question is, how do you construct this controlled unitaries, right? Because what I've just told you is I have to be able to have this controlled operation acting on an arbitrary unitary. And the arbitrary unitary is some sort of many-body wave function simulation that I'm trying to run. How do I construct a control on top of it? This is the next question to ask, and the last question to ask.
Yeah, so we have 10 minutes.
Yeah, I'll be done in a minute or so, I think. And so the solution to that is basically was proposed by a group in Australia in 2011, and their solution I'm just showing you in front. I'll just explain it in words. What they basically say is, imagine that you have a gate which they call the XA gate, and they show you how to construct this for atomic systems and many other implementations for linear optical systems. So what this XA gate does is basically, if you give it the state 0, it takes it to the state 2. If you give it the state 1, it takes it to the state 3. So imagine a 4-level atom, right? And what this XA does is, if you apply the XA, it takes you the quantum state in the lower 2 levels to the upper 2 levels. And if you don't apply the control, then it leaves it in the lower 2 levels. So using this, you can basically just move the quantum state physically out of the subspace in which you're performing operations. And so you can basically compute unitaries, control unitaries that way. So it's a very kind of classic solution that I just present to you very briefly. I won't explain too much more of it. The only question that I want to address basically is to ask whether the complexity of the controls is incommensurate with many-body dynamics, and the answer is no. So it actually only demands basically a polynomial number of gates in the number of controls that you want to apply. So suppose I want to have a complicated quantum system, and basically I want to have 10 leads in, 10 leads out, then I need essentially 10 of these controls in the beginning and the end. So it just scales like 20. It doesn't scale like e to the 20 or 2 to the 20. It just scales like 20. So it's a much simpler, it's much more favorable to actually construct this on. So let me just again, for the purposes of the colloquium, I didn't want to complicate the affair too much. What is the NISQ about in this entire story? So what is a noisy intermediate scale quantum computer? It's akin to the things that you can see right now in the news. So this is a picture of a Google Sycamore processor. It's one of the recent quantum computing architectures that made a splash in the news, commercial platforms that made a splash in the news. And so basically, what physicists and folks who are working in quantum computer science have been asking themselves in the recent past is, you have these kinds of quantum systems that are becoming more and more available, and can you do something with it? Can you do something interesting with it? And essentially what our solution is trying to propose is that you can take this kind of a quantum computer and you can put it to use to do quantum control theory. So the things that you have to basically convince the reader about when you make a proposal based on NISQs is the noisy part. So here is a kind of little cartoon I drew. It's not anything serious, but the cartoon basically is trying to say that suppose I'm trying to implement a true control field, BK, which is true. But any measurements that I make, all of this interferometric estimation, all of this stuff that I'm talking about, it's not going to be basically clean. It's not going to be the true magnetic field that I'm going to estimate. The time series is going to have noise from all kinds of different places. And so if you model the noise as basically just standard white noise, then you can show that the stochastically averaged cost function actually has monotonic convergence. And what that technical statement, what it means in words, is basically that even though you are running this quantum computer again and again and again to estimate even one point on the data set that you want, Each run has its own intrinsic errors attached to it, and the errors cancel out to first order. So you don't have to worry, basically. This thing will run, basically, will produce the solution that you're looking for. Okay, so just one or two more concluding thoughts. So do we break computational complexity theory? This is a question that I think is relevant if you're thinking about it, but not really if you're not. The only thing I want to say is computational complexity theory is another powerful way of thinking about the physical universe that we live in. So if we broke computational complexity theory, then almost always we should be satisfied that we are wrong. Basically, we should be saddened that we're wrong. I'm happy to report that actually, no, we don't break computational complexity theory. We actually need many copies of the target state to produce the thing. And what that means is that it's already bound by whatever optimal speeds that are existing for producing target states. There is no underlying algorithm that can be run in exponential time in real life. So problem there. All that we may do is shave some polynomial orders out of the problem. So instead of running something basically as n square, we may run it as n or something like that. I'm not even sure, but it's nothing that is very that is going to alarm a quantum computer scientist. But it's something very important for decoherence mitigation and for practical experimental quantum computation, right? And the other thing is that any such protocols have to be channel capacity compliant and quantum speed limit compliant, which is some technical stuff that I'll just let be for now. The other question that we wanted to ask ourselves is, do we break adiabatic quantum computing? And no, we don't. Another way in which we could check whether we're wrong. Adiabatic quantum computing is trying to find the ground state of a Hamiltonian, an unknown ground state of a Hamiltonian. We need that as the input to our algorithm if you're going to try and drive towards that as the target state. And so again, there is no particular compliance issues there, I don't think. So here are my conclusions. So I just want to conclude by saying that what I've presented to you is a technique that can also be generalized to GRAPE, which is a technique I haven't presented to you. But so all gradient-based optimization methods, basically, we can move them onto quantum computers. So I think this is a first step in basically what could become a very powerful bootstrapping method, where basically quantum computers can optimize themselves. They can figure out what the optimal computing schemes are to, let's say, run a compiled Grover search algorithm, so on and so forth, in real time, basically. And it requires some technical bits, like this superposition of the linear. It requires these linear XA gates, which are experimentally been demonstrated. They require basically extracting overlaps using modified swap gates. So there are some technical requirements for this. I just want to conclude by saying that we should all remember that we have to run this for every instant of time that you want to compute the overlap function. You have to run it 10,000 times to get the averages. So first of all, it's not particularly elegant in terms of trying to find the time series, but that's owing to quantum mechanics and not owing to anything complicated. So it's just the fact that expectation values in quantum mechanics, you have to repeat the measurements to extract them. And I'm happy to report that we believe that it's also robust to Hamiltonian noise. Okay, so with that, let me just thank you and take any questions.
Thank you, sir. Sai. I clap for the other people. So I posted the Jitsi room link in the chat box. So hopefully, if somebody have a question, they will enter the room and ask the questions directly. But let me anyway ask a question, which is I wanted to ask. So you showed us this nice system where you have this density matrix 2, 0, 0, -2. So
Yes.
which can imagine that this is a system which is like a 2x2 system. So I can think of it
This
as
is not the density matrix. This is the density matrix. So this is the density matrix.
yeah, sure. So this is the density matrix which you constructed out of it. But what I wanted to say, this is a two spin, like have some superposition there in some superposition, and then what you wanted to do. So this is just the control field, or this is the Hamiltonian that allow you to, means by control I mean that you have a state and then another state, and you want to go through within this Hamiltonian to that state, right?
So you can think of this as, some transverse Ising model or something. I mean, you can think of any kind of many body spin chain. with basically just a Z field switched on, a giant global Z field switched on. So
Right.
it's Z1 plus Z2 plus Z3, sum over sigma Zi times a J B of t outside. So this
Mhm.
is the control that you have in your hand. So this is just a toy problem that I'm pointing out.
I see. I see.
And
I
if
see.
you have this kind of a control, then what I'm saying is to extract the correct information that you want,
Mhm.
of which is basically this little thing that I'm highlighting with my cursor.
Right.
What you need to do is construct this operator Romeo.
Okay.
And once you construct this operator Romeo, you actually need to construct this overlap operator. So what you do is you basically construct an interferometric circuit like this, and you
Mhm.
keep supplying Romeo to one arm, and there are three arms now, not two. You supply Romeo to the middle arm. To the upper arm, you supply basically one wave function to the state, and to the lower arm, you supply the co-state. If you do that, then what happens is that the state goes in one arm. The second arm, instead of mu, it has this density matrix rho mu, which is a
Mhm.
physical object that can be constructed on a computer. This is the point I want to make. And the third arm has this chi, and you can compute its overlap by just using the exact same swap test. So you can construct this, you can construct this, and by doing that, you can extract this information. The problem with this information is that this is not a physical quantity. It's not
Mhm.
it's not something you can encode onto a quantum state, but it's linearly related to something you can encode onto a quantum state. So
Mhm.
that's it. And
Okay.
let me just say one more thing, Shomo. At least for these low examples that we worked out, these are all mixtures of local quantum states. So the
Right. Right.
rho mu's are efficient to prepare. They're not basically, if they're hyperentangled or something, then you can forget about it, because just preparing these rho mu will take you the next 10,000 years, and you're not going to solve the problem. So
Okay. I
there
think
are inherent
Sumiran is.
limitations to
Mhm.
our technique.
Yeah. So I think Sumiran is in the room. So can Sumiran, can you ask whatever you want to ask?
Yeah, I had just a small question related to that. What I asked is, so in this, what you described, the constraint on B was never implemented explicitly, right? I mean,
No,
even into
no.
the
Yeah.
statement of the problem, you said it can be implemented. Here, it is arbitrary.
Yes.
Anything can happen. Okay.
No. So one constraint is implemented, which is that it's a minimization over the set of all these, that basically will get you the solution. So it's a fluence minimization, but it doesn't have bandwidth constraints. So it constrains the amplitude, but it doesn't constrain the bandwidth. To do bandwidth constraints is a more complicated problem, and I don't know how to do that, to be honest.
Yeah, I mean, so fluence is just the integrated of B square, right?
Yes.
But at any moment, B can be anything in this scheme, right?
No, B square, basically what that means is that it selects for the magnetic field, which gets you the control solution that you want with the least amount of absolute magnetic field spent. So I mean, so, and even in solutions that for solvable problems on a computer that you can see, the magnetic fields are very modest, I must say. I mean, in comparison to other gradient optimization methods. So if you just use MATLAB's FMinCon or something like that, just a standard kind of, you just try and optimize for then you get incredibly large magnetic fields, whereas Krotov produces fairly modest magnetic fields. I agree with you, Sumiran, that this does not solve the problem. Can I just say one more thing, which is the reason why we basically didn't bother with this? The way to solve this, so the way experimentalists solve this right now, if you ask experimentalists who deploy quantum control, what do they do? Because they have bandwidth restrictions automatically. I mean, they can't just apply any magnetic field that they want.
Mhm.
What they do is they basically put a filter function on either Krotov or other gradient methods. So what they do is they solve the unconstrained problem. I alluded to this, so let me just say what this is. They solve the unconstrained problem. The unconstrained problem, let's say, has is has terms which are outside the bandwidth, allowed
Mhm.
bandwidth. They just chop it off and feed the chopped solution back into the algorithm. So the algorithm over time realizes that this high frequency terms are not doing anything,
Mhm.
and automatically just kills them. And so this is basically you can do grape plus filtering. This is called. And if you do grape plus filtering, then in the long time limit, you can actually see that grape actually just throws away those high frequency terms. Outside the bandwidth, it doesn't actually even just produce anything interesting. So it suppresses those terms naturally. So you can do the exact same thing here. Instead of constructing a synthetic filter on a computer, you just feed it whatever you can, and just you construct the interpolation of the high frequency, So you know what I mean. You just feed it the thing that you know you can, and then it'll cut out the high frequencies. In the first iteration, it might produce unphysical results, beyond bandwidth results, but the steady states typically follow this kind of mantra.
I see. Okay.
So that's the reason we weren't very worried about this.
Okay.
I see.
So, Smiran, if you do not have any other questions, there is no one entered in the room. So I have one last question. So, so what is the kind of the record right now with this algorithm, in a sense that what is the largest system size? Because we know that is exponentially hard in terms of system size. So for the many-body problem, I'm saying that what is the largest system size it can do within the reasonable and so on.
I am not sure, but let me, because I haven't thought with this point of view, but let me say that there are people already make shortcuts before they get to this.
Mm-hmm.
So what they do is people have proposed quantum control solutions with cold atomic systems, and there what they do is they take the kind of large end limit, and then they move to Gross-Pitevsky, and then Gross-Pitevsky is easy to handle. So people have been working with these kinds of, so essentially mean field type solutions people have produced, and there is a large success story with some amount of control that they have been able to implement. So with trying to simulate the full Hilbert space, typically people do things like tensor networks. So people have incorporated basically tensor network techniques right into basically these kinds of control, because it's just a simulation, and you run the simulation by doing tensor networks, and you refeed it in. So these are the two I know, but I don't know the exact number of what the largest size was.
Okay. Thank you. So let's check the YouTube. There is no questions yet. So okay, thank you. I think we can end the session today here. I would like to thank
you very much.
everybody who joined, and again thank you, Sai. So let me clap once more for you.
Thank you very much. Thank you very much.
And for the other people, yeah, thanks, Samiran. For the YouTube viewers, I again thank you, all of you, for joining, and we'll meet next week. All the best. Bye-bye.
Bye-bye.